Okay, so let's tease this out a little bit more. We have the reaction quotient, and we have the equilibrium constant, and we know that equilibrium, they're the same, right? Now, we also know that at the beginning of a reaction, when the products are zero, right? If the products are zero, Q is going to be small, right? So we could say that QC, when QC is less than K, the reaction is going to go in this direction. Now, we could say the opposite, right? We might start out a reaction where we had a lot of C and D, but no A and B, in which case QC would be undefined, right? You'd have 0 down here if there was no A and B. So anything over 0 is going to be undefined, right? But once we got some A and B, QC would be very, very big, right? If this was close to 0, this quotient is going to be very big. So when QC is greater than K, then we know the reaction is going to go in the other direction. All right, so we're going to tease this out just a little bit more. A system that's not at equilibrium will proceed in the direction that establishes equilibrium, of course, right? Because we're always driving toward equilibrium. So by comparing Q and K, it is possible to determine which direction the system is going to go. Let's consider this more. When Q is less than K, that means this appears too small, right? When this quotient is small, that means the numerator is too small, right? And so therefore, we're going to need more reactants. The reaction is going to go in that direction, right? Now, when Q is too big, that means we have too many products, right? That means it's going to go back toward the reactants, right? And when Q is equal to K, that means we are at equilibrium, and it's not going to go in either direction, okay? So there are many ways to approach the equilibrium state with this. Let's consider this reaction. There are many ways to approach the equilibrium state. First of all, you could just simply start with A and B, right? Carbon monoxide and water. Or in a different scenario, you could start with just carbon dioxide and hydrogen gas, right? In which case you would mostly be going that way, right? And then a third possibility is you could start with all of them, okay? The value of the equilibrium constant doesn't matter what you started out with, right? Because it's the ratio of the products to reactants, which is the constant, okay? So let's suppose in mixture 1, if you start out with only, I think in mixture 1 we were saying we're only going to start out with the reactants, okay? Then we might say, all right, well, if we start out with only reactants, we start with about with this much of both of them. Well, it turns out at equilibrium, we're going to have just a second here. At equilibrium, this is before the reaction starts. I was saying that wrong. Say this is before the reaction starts. We have, let's say, 0.0243 moles per liter of both of the reactants. That is these two, right? The carbon monoxide and water. Now, in the second scenario, mixture number 2, let's say we start out with this much, 0.0468, just making up numbers, right? 0.0468 of these two, right? That's the products. And in mixture 3, let's say we start out with these amounts, okay? These are just 3 scenarios, right? All right, that's before the reaction begins. Now, at equilibrium, we're going to have the same ratio of the products to reactants. And so it turns out if we find out that K is 0.640, and we would look that up it would either be in the question stem or we would look it up in a book somewhere, right? If at equilibrium Q is going to be equal to K, if the ratio is 0.640, then that means we are going to have 0.0108 of these two and 0.0135. I did not show the math here, okay? Just showing that the ratio is the same. Now, since we started with more in mixture 2, the ratio is going to be the same, right? It's still going to be 0.640, but we're going to have different actual amounts, right? And again, the ratio is the same. If it's at equilibrium, remember we said that? It's at equilibrium, then the ratio is going to be the same. And it doesn't matter what we started out with. The ratio is always going to be the same. I did not show the math. How did we get these numbers here? That's coming up, We haven't done that yet. Just want you to appreciate that the ratio at equilibrium is always the same. If Q is too big, the reaction goes toward the, that means we have too many products, the reaction is going to go toward the reactants. If Q is too small, then we don't have enough products and we're going to go toward the products or go to the right. And if Q is equal to K, then we're already at equilibrium. Okay? And here's the, I think, really clutch rule here. A system that is not at equilibrium will always proceed in the direction that establishes equilibrium.